Good morning, students. Today I want to discuss examples on linear differential equation with variable coefficients. Till now, we have discussed the examples and how to solve the differential equations with constant coefficients. Now, there are two types of linear differential equations with variable coefficients. Today, first one I will discuss with you, that is Cauchy's linear differential equation. The differential equations of the form a naught x square d square by dx square plus a1 x dy by dx plus a2 y equal to phi of x are known as linear differential equations, Cauchy's linear differential equations. Here, one thing we can observe here, why we are calling it as a variable coefficient. The coefficient of derivative dy by dx is x. In previous classes we have discussed there is only a1, but here one x is present. D square y by coefficient is x square. Like that, if third order differential equation is there, its coefficient d cube y by dx cube coefficient will become x cube, and so on. Such differential equations, the first order derivative, its coefficient is of the power 1, second order derivative, its power is 2, and third order, if it is present, third order power, that is x cube. Such differential equations are known as Cauchy's linear differential equations. To solve such differential equations, we have to convert this differential equation with constant coefficients. To do that, we are going to substitute z is equal to log x or e to the power z is equal to x. Then x dy by dx will become capital D into y. What is it capital D? Capital D is nothing but d into dy dz. X square into d square by dx will become capital D into d minus y. Here you can observe here the coefficient is becoming constant. X instead of x, it is becoming constant. X square instead of it becomes constant. X cube, it also becomes constant. Then how we have got this formula? These three formula you have to remember. Let me explain this how we have got this first, then let me solve the problems on this. Just consider a Cauchy's linear differential equation of this type. To convert it into differential equation with constant coefficients, just we are putting z is equal to log x or e to the power z equal to x. Then if you differentiate this one with respect to x, dz by dx will become 1 by x. Remember this, dz by dx equal to 1 by z. Now I want to substitute for this x into y dash, x into dy by dx. Consider this y dash. Y dash is nothing but dy by dx. Dy by dx, by chain rule I am converting it into with respect to z. Therefore dy by dz into dz by dx, multiplying and dividing by dz. Then here dz by dx I know that is equal to 1 by x. If I substitute this and shift it to the left hand side, it will become x into y dash. Then we will remain with the dy by dz. Therefore dy by dz, d is replaced by d by dz, differential operator. Therefore x into y dash will become d into capital Y, where d is d by dz. Therefore we are converting variable coefficient to a constant coefficient by substituting x into y dash equal to capital D into y, where x variable is eliminated, z variable has introduced. Similarly, how to get the second order x square y double dash, differentiating this again with respect to x, we will get x into y double dash plus y dash, which is equal to right hand side d is nothing but dy by dx, differentiating with respect to x, dy by dx. Again here keeping this as one term, again by chain rule multiplying and dividing by dz. Therefore d by dz of dy by dx will become d square by dz square, and dz by dx is 1 by x. Substituting, then again shifting this to the left hand side, x into x y double dash plus y dash equal to d square y by dx square. Then multiplying this x square y double dash, x y dash shifting to the right hand side, xy dash. Therefore again replacing d square by dz square equal to d square. D square by dz square will become d square, differential operator, minus this already we know this is a capital D into y. Therefore taking y common and d common, d into d minus 1 into y. Further, for higher order like that, x cube y double dash if it is there, then we have to replace it by d into d minus 1, d minus 2 into y. If it is a fourth order, if it also present, d into d minus 1, d minus 2, d minus 3 into y. Then after substituting these things in the given differential equation, that will reduce to differential equation with constant coefficients. Now let me solve one example on this so that you can understand clearly how we are converting it into with constant coefficients and how to solve by the previous methods. Let me consider x square y double dash plus 3x into y dash minus 4y equal to 2x square. Simple example. And you can observe that in previous problems y dash coefficient was constant, but here it is 3x, x was there. Y double dash coefficient is x square. Therefore such equations are known as Cauchys linear differential equations. To convert this one into with constant coefficients, let me put z is equal to log x and or e to the power z equal to x. By substituting these, what I will get, x y dash I can replace it by this x y dash, I can replace it by capital D into y. X square y double dash can be replaced by d into d minus y. Already we have proved, I have shown this formula. You have to remember this formula for Cauchys. Substituting in the equation, I am getting d into d minus 1 into y, 3 x y double dash is x y dash is d into y minus 4y, and right hand side also you have to substitute. Don't forget to substitute that. Right hand side also you have to substitute 2 into here it should be 2 into x. X value is nothing but e to the power z. Therefore e to the power z the whole square. Therefore 2. And here e to the power 2z I can write. Therefore here simplifying this, d square minus d and taking y common, 3d minus 4. This equation will become the differential equation with constant coefficients, whereas capital D is nothing but capital D equal to d by dz. X we have eliminated from this equation. We have got this equation in the terms of y and z. This equation we can solve by the previous methods. Now auxiliary equation for that equation is given by m square, replacing d by m, that is m square plus 2m minus 4 equal to 0. Then the roots, how to find this equation already we discussed. You can use a calculator to find out its roots, or another any method, product should get minus 4, or that formula x m equal to minus b plus or minus square root of b square minus 4ac whole divided by 2a. This formulas you can use, or using calculator will get these two roots. m1 equal to minus 1 plus root 5, m2 equal to minus 1 minus root 5. Distinct roots. Therefore I can write y1 yc complementary function equal to c1 e to the power m1 z I am writing here, not x, because our differential equation has converted in terms of y and z. That's why it was z. C2 e to the power m2 into z. This is our complementary function. Next, particular integral 2 into e to the power 2z divided by f of d, d square minus 2d. And we know that it is type 1 e to the power 2z. Therefore, replacing in this d by this coefficient 2, then we'll get 2 into e to the power 2z divided by 2 square, d is replaced by 2 square plus 2 into 4. Therefore 2 into 2 4 plus 4 minus 4 cancels. 2 into e to the power 2z divided by 4, 2 1 2. Therefore our particular integral will become e to the power 2z divided by 2. complete solution is given by y equal to complementary function plus particular integral, complementary function and particular integral. But we want the solution in the form of y and x. Again substituting back for z, therefore c1, this I can split using a laws of indices. E to the power mn I can write it as, or a to the power mn I can write it as a to the power m to the power n, or reverse also. Therefore e to the power z to the power this one, e to the power z to the power minus 1 minus root 5. Here also same thing, e to the power z the whole square. I know that e to the power z, we have substituted e to the power z is equal to x. Therefore y equal to c1 e to the power z will become x, c1 e to the power and e to the power z will become x square. This is my complete solution in the form of x. Thank you.